Okay, so we're looking at maximum and minimum values now of a graph. So let's look at what we have before us. We have a definition of absolute maximum and absolute minimum. So let f be a function defined on some interval I. If there's a number u in that interval I for which f of u is greater than or equal to f of x for all x in that interval I, then f has an absolute maximum of u, and the number f of u is the absolute maximum of f on I. So basically, if we have some interval, looking at this, and let's say, because it said f of u, so let's say x equals u, we have some point here. And on this interval, this is defined everywhere, and the maximum value here occurs when x equals u. The y value, so max occurs at x equals u, but the maximum value is actually the y value. But the max value, so if they ask you what is the maximum value or the minimum value, it's always the y value. So I can represent that y value when x is u as f of u. So similarly, we have the same thing for absolute min. If there's some number v on an interval I, which f of v is less than or equal to f of x for all x on I, excuse me, then f has an absolute minimum at v, and the number f of v, that y value at x equals v, is the absolute minimum of f on that interval I. So maybe we have some value v over here. And if we look at this interval, any interval around here, and it's defined for it, all the y values are bigger than this y value when x is v. And so we have a min occurs, or minimum value occurs at x equals v, but the minimum value is the y value, which we can represent as f of v. Okay, so having that definition, let's look at the following example or examples. So we have a graph in front of us, the one on top, and it asks us the numbers, if any, at which f has a local maximum. What are the local maximum values? Okay, so local maximum. I noticed that we have a local maximum right here. There's some interval where that's the highest value. And so x equals 0 is where a local max occurs. But the local maximum is f of 0, which is 2. Okay, so do it for local minimums. So if we look at it, this is the smallest y value on that interval, some interval. And so at x equals -1 and x equals 1, we have local mins. We have local mins. And the local mins are the y value there is 0 for each one. So we can do this similarly to the graph below that. We can find out where our max and our min values are. And so if I look at the max, I notice that I, again, only have one peak. And so we have a max at x equals 0 of the maximum y value is 1. We have a min, there's a couple of them. And it looks like when x equals negative pi and x equals positive pi. Of that y value that we're hitting says is -1 on that point. So that min value of -1. Okay, so there's an important theorem, and this is a theorem actually that I just covered in calculus, and we can't prove this until you get into calculus. That's something to look forward to. And the following is the extreme value theorem. So we got this extreme value theorem. And so what the extreme value theorem says, if you have a function f is continuous on a closed interval a, b, then f has to have an absolute maximum and an absolute minimum on this a, b. Okay, there is this condition here that it has to be continuous. So this is, again, another thing that you can prove in calculus what it means for a function to be continuous. For us, though, in order for a function to be continuous, it has to be smooth. Well, it doesn't have to be smooth, it could be jagged, but there could be no jumps in the graph. So if I had something here where I have to lift up my pencil or pen to graph it, that's not continuous at that value. So it's telling me if I have some closed interval and it's continuous on that closed interval, then it has to have an absolute max and an absolute min. So absolute max and absolute mins are the largest y value or the smallest y value that occurs on the graph. So let's look at this extreme value theorem and see if we can find an absolute max and an absolute min. So looking at the following, and let me just read what that had stated. So in the directions, let I grab that, maybe not. It says, for each graph of the function y equals f of x, find the absolute maximum or absolute minimum if they exist. Identify any local maximum or values or local min values. Okay, so looking at this, we want to see, is it a closed interval? And notice that here we have a point here, so it's closed on the left-hand side, and we have a point here, solid, and it's closed on the right-hand side. The graph doesn't continue on past that. If you look at everything between the x value 0 and 5, notice that it's continuous everywhere. There's no jumps in the graph. There's no holes in there. And so the extreme value theorem should hold. And if we look at the absolute max, well, that occurs at the value of x, which gives us the highest value on the graph. And so if you notice here, the highest value that the graph reaches is at this peak. And so we're going to look at what is the x value of that, which it tells me because it has the point right here. So we have an absolute max of 4 because that's the highest point. So the max is 4, absolute max of 4 at x equals 4. The absolute minimum, that is the smallest y value that we hit on the graph. And so notice here, the smallest y value that I hit is at 0. So our absolute min of 0, and that occurs at x equals 5. If you look at this, I have another minimum value. It's not the smallest minimum value, but if I look and take the interval around that, that's the smallest value for all the y values there, than all the ones around it. And so we do have a local min at x equals 1. And that min is 1. Local max, local mins, or absolute max, absolute mins, if we have this closed interval, which we do, could occur at our n values. So in this case, when I'm looking at when x is 0, notice that that's the highest value along this interval in here of where it's defined. It's not defined for x less than 0, but for x bigger than 0, in this little interval in here, it's always this at x equals 0 is always bigger y values than those. And so I can say I also have a local max at x equals 0 of a y value of 2. So looking at the next graph, it wants us to do the same thing. Is there any absolute max or absolute min in here? Local max, local mins. If you look at this, I can see that this is continuous, but I'm not on some closed interval. There's this vertical asymptote here at x equals 3. And so I'm getting closer and closer to this x equals 3. I'm hugging this. This is shooting down to negative infinity, but I'm never going to cross this x equals 3 or even touch this x equals 3. And so I do not have an absolute min. Let's look for local mins though. So looking at this right here at x, that 0.02, I have a local minimum. So local min so the local minimum value is your y, which is 2 at x equals 0. If I look at this 0.24, notice that's the highest point on the graph. And that's actually the highest y value I'll reach because this has a solid point here. This is not continuing on forever upwards. And so I have a absolute maximum of 4 at x equals 2. Absolute max are also considered to be local max. If I look at my endpoint, because I do have an endpoint here, this is going to be a local max. So I have a local maximum at x equals -1. And the y value, the local max is 3. Okay, so one more like this. So looking at the graph again, identify if any local max, local mins, absolute max, absolute mins. if you notice this graph, that extreme value theorem cannot hold. It's not continuous everywhere. We do have our endpoints. So we do have a bounded interval between -1 and 3. But notice that at x equals 1, you have this open circle in here. And at x equals 2, we have this open circle in here. And so there's no biggest value that we're getting there at 1, 3, because it doesn't exist. So I can get so close, and this is another concept from calculus, I can get so close to x equals 1 on the left, like 0.9, 0.999, 0.99999. And every number I put in there, I'm getting closer and closer to this y value of 3, but I'm never reaching it. So there's no value of x that's giving me this highest value. Because if you give me 0.99999, I could just give you 5 other 9s after that. And I would say, hey, oh, that's higher than yours. And so we could keep playing that game. And so there's no absolute max. And then same thing with my minimum value. It looks like if that was a point at 2, 0, that would be my absolute minimum, but that's not a point. And I can get closer again on the left and the right, and I could always find left to right of 2, and I could always find some x value getting closer to 2. That would give me a smaller y value getting closer to 0. And so we have no absolute min value. But if I want to look at, do I have any local max or local mins? Well, look at it, x equals -1. If I look at the interval where it's defined, so anything bigger than -1, close to it, that at x equals -1 is going to give me the smallest y value there on that interval. So x equals -1 is a local min. Is where a local min occurs. So x equals 1 is the local min. Not x equals 1. Sorry, x equals -1 is where the local min occurs. I can do that same sort of reasoning for my right-hand endpoint on that graph here. So at x equals 3, notice that at x equals 3, that's the highest value, y value on some interval around it where it's defined. And so at x equals 3 is where a local max occurs. And that local max is the y value, which is 1. So that local min was the y value of 1. So a local max and a local min in there is giving us back the same y value.